Well, hello, here we are again. It's the psci 168 video lecture. psci 168 video lecture 3. And a lot of interesting stuff today. We're going to pick up where we left off in terms of the geometry and do a few more things, circle and square, and I want to do some applications of similar triangles. And we'll end up attempting to measure the shape and size of Earth. Shape and size of Earth. Now, before we get to that, I'll have an announcement or two. So let's see. We had for arithmetic, we had scientific notation. Well, there's a really interesting, somewhat famous video called Powers of 10 by Ray and Charles Eames. This is from 1977. So video, Powers of 10, that's what it's called, by Ray and Charles Eames. That was a husband and wife team. Eames, okay. And I located the video and put it right in our psci 168 playlist. So I think it's about 10 minutes or so. And you're going to want to have a look at it. It's amazing. It's a very great classic video. About powers of 10, namely the idea of zooming out from the Earth all the way to the outer reaches of the universe, and then zooming back in and into the human body and into the innermost parts of an atom. So it's excellent. It'll make you appreciate scientific notation and the powers of 10. So what you do is you view that video and see if you're able to pull out a nice screenshot to print out for your collection, right, for your book. And you'll definitely want to, make a note of that video in your lecture notes. I have it right here. And see if you can get a screenshot. So homework, a screenshot for, that's a T, screenshot for your notes, or for your notes/book. And another thing, I just attempted to locate the transcript. And I failed to. Luckily, I have kind of a bad copy of the transcript. And if I can't find it online again, I'll make a copy and email it to you guys, okay? I'll make it available to you, because the transcript, namely the spoken text of the video, is also very interesting and beautiful. It's a little too much to even take in all at once, so having a transcript would be nice. So I'm just going to write here transcript question mark. We'll see what happens there. I was not able to locate it. I've printed it out in the past, but you can try finding the transcript too. If you find it, you'll know it. Good. So this video here, I've often showed to my classes, and you guys will just be able to see it in the playlist, 5 or 10 minutes long, something like that, and then have a look at it and see what you think. Okay. So that is the one announcement, and next we're just going to start off with, or continue on with, some geometry. We ended with the Pythagorean theorem. I have given you some facts about geometry, circles and squares and stuff like that, rectangles. So what I want to do is discuss the circle. The circle and the number pi. So the circle is the set of points that are equidistant from one single point, which we call the center of the circle, and then we have a radius r. So circle, radius r. And the question is, what is or how long is the circumference of a circle? Okay. Circumference of a circle is some multiple of this r here. You can imagine if I had a string the length of r and I could go around and measure and get the entire circumference of the circle. The number pi, which is the Greek letter pi here, and if you look it up on your calculator, you get 3.14, and goes on and on and on. Okay. What's the definition of pi? The definition of pi is actually, it's a ratio. It's the ratio of the circumference to the diameter. And so for any circle, it's the same ratio. So that's why it's just a number. Here's a length and here's another length. Length divided by length is just a number. So it's that ratio, or you could say it's the ratio of the circumference divided by twice the radius, because the diameter is twice the radius. So we have circumference is equal to 2 pi times radius. That's a formula. And but really, this is a formula that defines pi. Okay. So we have the circumference of the circle. And now the question is, what's the area? What's the area bounded by the circle? Area bounded by the circle. I'll show you a construction here. Construction. That's pretty interesting in its own right. I told you the other day, and in fact, didn't I have, right, I had a, this is something we've often done in this class, got a cutout here. Here I've got a cutout square and a cutout circle. Cardboard. Square and circle. I'll use that. Good. Square and circle. And in fact, I've made these so that the square circle fits right into the square there. That means the square has a side of 2 times r. Okay, 2 radii is the side of the square. Let's go ahead and draw that. So we have circle and square. This is one of these projects we actually do in the class for teachers. So feel free to do the same thing if you're so inclined. Cut out a circle and a square. So here's a circle of radius r. So clearly the square is of side 2r. I have a circle and a square. Now, the area bounded by the circle, I'll go ahead and shade it in red. Right, there's the area bounded by the circle, clearly less than the area bounded by the same square, right? So we have area sub circle is less than the area sub square, as discussed right here, and the area is bounded by the square is 2r, the quantity squared is equal to 4r squared. Okay. So the area bounded by the circle is less than 4r squared because we have this extra area. How about I put a little blue here, color into our notes. Right, there's the extra area that makes up the difference. Okay, it's less than 4. What is the area? It's less than 4r squared. So what is it? There must be some number that comes in front of the r squared. Now, there's an interesting construction that will allow us to get this area of the circle, and I think I can fit it right on the board here. So let's draw another circle. There's the center, and we're going to do the following. We're going to draw a triangle here, like a slice of pizza, and a larger one would be nice, but this will be fine. Actually, I've been meaning to tell all my classes, you possibly already know this, if you're viewing these videos on your, say, your laptop computer screen, and you have full screen for the video and you have the high resolution for the YouTube video, then I've seen that everything's very, very clear and legible. So if you're not aware of that, you can adjust the the video resolution. It doesn't necessarily come up high resolution right away. You go to some little toolbar, bring the resolution up to high resolution, and then you'll see everything. Okay. Yeah, so there's a triangle. It's like a slice of pie, right? And I'm going to draw it in red in the following sense. We're going to extend it out a little bit. Okay, so now I've got this triangle here. Okay. And imagine I were to fill in a bunch of triangles, kind of like I would encase the circle, instead of in a square, in a whole sequence of these triangles. Okay. All outside and then the question is, it's very clear that the area bounded by the circle is less than the area bounded by this red polygon. Okay. But we can get a wonderful estimate on this now. So the area bounded by the polygon, which is in red, goes all the way around the circle there. The polygon is equal to the sum of triangles, by which I mean the sum of the areas of those triangles. Now watch this. Sum of, we can use the Greek letter sigma as a symbol for sum of, uppercase sigma. Let's go ahead and draw that nice. Okay. Sigma's not looking that good then. Once more with feeling. Boom. Okay. There's the sum of, and what is the area of one of those triangles? The area of one of those triangles is 1/2 base times height. Each triangle 1/2 base times height. Now watch this. Sum of 1/2. The base, I'm just going to call it the base, but the height of this is of course r. The height of that triangle by construction is r, so 1/2 base times r. Let's go ahead and put this in here. See, I need more board. No problem. Actually, I'm going to leave this definition up. In your notes, of course, you just continue on. There's this definition up here. So I'm continuing down here. Area bounded by the polygon is equal to. Now, the 1/2 is a constant, it can come out, and the R is constant for the circle to come out. So it's now the sum of the bases of all of those triangles that go around the entire circle. But the sum of those bases is approximately equal to the circumference. So that's an approximation sign. Circumference. And the circumference is equal to 2 pi r. Okay? So what I end up with is 1/2 r 2 pi r. And the smaller I make these triangles, the more accurate the answer is. And in mathematics, we would say in the limit as those triangles become infinitely small, and there's infinitely many of them, we would get the exact result. So I'm going to just leave this up as that proof there, but you can see we're going to get a cancellation of the 2's. We're going to have pi times r, pi r squared. So the area bounded, so I'm just going to write area A is equal to pi radius squared. Now this is a beautiful construction that you may want to look at a little more. So there's a formula, you find it in any book on geometry, and this is how it comes about. Still doesn't answer the question of what pi is equal to. Okay, we haven't answered that question yet. And there are different ways of getting at the answer more and more exact that we won't pursue anymore because we can't do everything. Okay. But that's how the area bounded by the circle is obtained. Okay. So if you take all of the things that we've done in geometry so far and practice them, you'll notice we're never really plugging any numbers in. We're always using symbols, and I want you to become accustomed to writing symbols, drawing pictures, labeling them, and manipulating the symbols with these algebraic steps. Okay. And you know, you can give me some feedback in your emails in terms of how difficult or easy you find this to be. But by no means be discouraged. We're making our way through this material at just the right rate. Okay, so now we've done some geometry, and I want to give us a very useful application of this. Useful application. Let's see, this is the last thing we did. No, we got that right there. So I'm going to go ahead and erase this board. Like I said, a little project that we've done in this type of class is to actually build these, construct these, cut them out of the very same type of cardboard, and then later on we would weigh them on a balance. That's something I'll do later, okay? And in a couple lectures from now. Okay, right now the application is an application with similar triangles. So here's the question. So let's call this application. We want to know how high is a tree. I often say a certain tree on campus, we'll just pick one. How high is the library? How high is that tree, that building? And here it is. So let's draw some tree here. There's a tree, and the question is, how high is the tree? Height of a tree, and This will extend to the height of a building, height of a mountain, height of anything you can think of. So how do we measure the height of that tree? Okay, what we do is draw a baseline over here. And suppose this is your me. You can measure your own height, can you not? Okay. Question is, what's the height of the tree? Well, I'm going to complete this as a triangle. Sometimes it's better to draw the triangle first, but I'll just freehand it. Not bad. Not so good either. Let's make that a little extended up to here. How about that? Sometimes you got to stand away from your work to see if it's coming out. That'll do. I will monkey around with my drawing a bit. There we go. I can erase this. And I can extend the... Okay, see what I'm doing. How high is this tree? Well, apparently there's a geometry problem, but it's a practical one. So I'm going to label these things as follows. H, capital H, is the height of the tree. Capital L is the distance from the base of the tree to the point of that triangle there. Now this point here could be the extent of a shadow that would be cast by the tree when the sun is shining on it from up here, right? The tree would cast a shadow that could be down to there. And I'm going to use lowercase letters, so H is my height here, and lowercase l is that distance right there. See, what we have is similar triangles. The small triangle with the lowercase letters is similar to the large triangle with the uppercase letters. And when we have similar triangles, we also have similar ratios. These share an angle, and we could say this ratio is equal to this ratio. So I'm going to write that out. We will say similar triangles. No, we don't actually need to have an angle in here, but you can see this angle characterizes the little triangle and the big one as well. Similar triangles, comma, so these two ratios are the same. For the big triangle, H divided by L, the ratio of this opposite and adjacent side is equal to this ratio H divided by lowercase l. You'll notice I'm not plugging any numbers in, but this is my height, this is distance of me to the end of that triangle, this is the height of the tree. So what's the unknown? What do we wish to find out? We wish to find out how high the tree is. So solve for capital H. Solving for capital H would just mean to multiply both sides by capital L and then cancel the L. I'm going to go ahead and do that a little smaller. So H over L times L, the lowercase times L, right? I multiplied both sides by the same thing. Here we get a cancellation. As a result, we have the height of our tree or building or mountain is H over L times capital L. And now the point is this. By the way, this is how all surveying is done fundamentally. You want to know the height of H there, you have to measure your own height and these two distances, but these two distances are on the ground. You have access to them, right? You set up your measurement right. You can measure these distances with a ruler, with a tape measure. You can pace them off, and then your unknown height of the tree is obtained here. So this is the principle of surveying. Local properties, buildings, townships, mountain ranges, all the way out to the earth itself, is done using triangles, where there's an unknown that you can solve for, and for more extended applications, you just extend the whole web of these equations. Okay, so this is it. We didn't even have to know trigonometry per se. We have to construct triangles. We have to know about similar triangles, and we're ready. Okay, so that's an important property, because our next task is going to be a little bigger. We're going to try to imagine measuring the size of our entire Earth itself. And then we'll have a handle on our environment. When we talk about energy in the environment is our entire Earth. We need to know how big it is. Okay, so these are some good applications. Now, what I did with my class when we're meeting is we also made a sextant with a protractor and a plumb bob here, and we could measure angles. We could aim at the top of the tree and construct triangles with different things and measure them out with a ruler. So we did a bunch of fun stuff like this. But if you want to apply this, go outside, see if you can document it, send it to me. I won't reject it. Okay, this is a good project to measure the height of something using this kind of knowledge here. And the main thing to do, if you do want to attempt this, is to draw a good picture of what you did and what you measured and what was unknown, and then you take it from there. It's not that I'm even going to give you the actual step-by-step. In this case, I want you to see what's possible and feel good about that. And also, these steps I'm taking, I definitely would like you to just do these. That's why I'm having you write the notes. Do them a couple times so you become more comfortable with this kind of thinking, okay? This kind of mathematical and physical thinking. Okay, let's consult the clock and see how long we've been going. Okay, that's not bad. We'll keep going a bit. But yeah, we're already coming up on 30 minutes, and you do want to have a look at that video. And did I give you any other homework? Looking for the transcript, getting a screenshot. Here, what I'm going to do is, nice thing is with the notes as homework, you always have something to do. Perfect your notes, and you'll be fine. Yeah, so here's what we're going to do next, and I'm just going to set it up now. Tell you what our next big project is. And basically everything is building on what we've done, and I'll continue to try doing that. So our next big project is to determine the shape and the size of Earth. If you didn't know it, if you just lived here in Fresno with no access to pictures, or if you were living in ancient times and you had to discover what shape the Earth has and how big the Earth is, that's what we're going to go through. We're going to discuss shape and size of our Earth. Right? Here's a meter. The meter stake, how many meters is, say, the radius of the Earth? But before we answer that question, how do we know the Earth is even a sphere? That's why it's a two-part problem. First, we're going to discuss the knowledge of the shape of Earth. How do we figure that out? And in fact, to talk about the shape of the Earth as an object, we have to even know that the Earth is a heavenly body. Right? If we look up at the sun and the moon, they're clearly spherical. Stars are too far away to tell, right? They're points of light, but the sun and moon are clearly spherical. So how do we know that the Earth is even a heavenly body? If it were on equal footing with the sun and moon, then maybe we would just guess that it's a sphere, okay? So shape of Earth, and here, a little note. How do we know Earth is a heavenly body? At all, okay? And then, having answered that, and of course we'll determine it's a sphere. Having answered that, then size of Earth, comma, its radius. Oh, it's a sphere, then we can talk about the radius. And that'll occupy the next hour, or part of the next hour. And after that, we're ready to start talking about forces and stuff. But you can see these questions build on these type of questions. And the concept of forces and its applications is also going to build on the geometry. So everything we're doing step by step, just always practice what's in the notes and become comfortable writing formulas, letters, sketches, and we'll keep making progress. Okay, so that's what I had to say for today. You've got the video powers of 10 that you want to look at. Get, so you can get a good screenshot off of it, or more than one, whatever you like. The transcript I'm going to do a search for, and if we can't find it online, I will try to make a copy of mine. It's a little ratty, but I'll try to make a copy of that, and I'll send it to everybody by email. And then you can put that in your book as well. Okay, good. So until next time, see you later.